So we're doing Unit 4 and 5 review right now with just a dash of Unit 6. So this is going to be probability. This is definitely one of the units people struggled with the most, or these units, plural. So make sure that you review this video carefully, especially if you struggled during either Units 4 or 5. So the first thing is the fundamental counting principle. The fundamental counting principle is where you multiply the number of ways each event can happen to get total possible combinations. This sounds fancy, but really it's just where you multiply the number of outcomes for the first choice times the outcomes for the second and the third. For example, the classic outfit problem. Susie has 5 pairs of pants, 12 shirts, and 3 pairs of shoes. How many outfits can she make? 5 times 12 times 3. There are 2 specific types of counting problems. There are, well, lots of types. Combinations and permutations are special types of counting problems. For both of these, you're doing this without repeats. But combinations is when order doesn't matter. Permutations is when order does matter. So you do n choose r or n pick r. Remember to find these features in the calculator. You go to math and then go over to probability. How many committees of 3 can be selected from 4 people? So in this case, order doesn't matter because it doesn't matter if you were chosen first for the committee or last for the committee, you still get to be on the committee. So we would use combinations. Order would matter if there were different positions on the committee. So we have 4 options and we're going to choose 3 of them. That's kind of mean. We're leaving just one person out. And when you type that in, you get 4. In how many ways can a class of 25 students elect a president, vice president, and secretary if no student can hold more than one office? So with this one, order does matter because there are different positions. Anytime there's different positions, order does matter. So we have 25 people and we want to pick, there are 3 offices. When you type that in, you should get 13,800. This is great. Counting problems can come in handy in life. However, I have not seen them on the AP exam ever, so they probably won't be on the test. They're good things to know, but they probably won't be on the exam. But they could be. Here are some basic probability definitions. The first is the complement. This is the probability the event doesn't happen. So for the complement, we have our event E inside the circle. The complement is everything outside of the circle. Remember the notation we use for this is like that. And that's going to be 1 minus the probability of E. The union is the probability event A or B happens. Venn diagram for this one is where we have the 2 overlapping circles, or can be in either circle. So I would shade everything in either part, including the middle. But the intersection is for and. That would be only the part where they overlap. So that part was included up here, but that's all it is for and. Mutually exclusive or disjoint is when 2 events have no outcomes in common, so they're completely separate. The Venn diagram for this one would be 2 separate circles. There would be no overlap between them because they're disjoint. They have nothing in common. Independent is where the probability of one event happening doesn't affect the probability of another event happening. There's not a fancy picture for that, but essentially if the first event happens, that doesn't change the probability that the second event happens. Things that are independent would include things like dice rolls. If you roll a die and you get a 3, that doesn't change your probability of getting a 3 the next time. But when you play cards, say you get a black card the first time, if you don't replace that card, your probability of getting a black card the second time has changed. So that means the second time, or that means that probability is dependent. A mutually exclusive example would be like getting a red card and a black card. You can't get both of those at the same time. A card is either red or black, it's not both. But you can get a card that's a red and a 2 at the same time. So a red and a 2 would not be mutually exclusive. Remember, disjoint events are dependent since the probability of one does affect the probability of the other. So if you know the first event happened, that means the second event can't happen. So that probability is now 0 and it has changed. The law of large numbers says as the number of repetitions of a chance experiment increases, the difference between the experimental probability of occurrence and the true probability approaches 0. So for example, if you're rolling a die, you expect to get a 3 1/6 of the time. If you continue to roll that die over and over again, your experimental probability should get close to 1/6. Some of the basic probability rules: the probability of A and B equals the probability of A times the probability of B, given that A has already happened. That's down here for what that symbol means. So for example, getting a spade, there are 13 spades out of 52. So that would be the first time would be 13 out of 52. But then the second time would be 12 out of 51. Versus if you're rolling a die and you want a 3, that's 1 out of 6, and then it's still 1 out of 6. So this is the same number. The probability of E or F equals the probability of E plus the probability of F minus the probability of E and F. And if we look back at our Venn diagram, we can see why. So remember, E or F is both circles added together. If you take circle E plus circle F, this part in the middle, the part in the middle is being counted twice. It should count, but it shouldn't count twice. It's being counted with E and with F. So when I do E or F, I do E plus F, but then I subtract the overlap. If there is no overlap, because E and F is 0, then there's nothing to subtract. The probability of at least 1 equals 1 minus the probability of none. So you take all of your, so at least 1 would mean obviously 1 or more. So it could mean, for example, if you're taking 5 things out of a hat, that could mean 1, 2, 3, 4, or 5 successes. And that's a lot of different orders to consider, but the opposite of at least 1 is 0. Because at least 1 means greater than or equal to 1. The only thing not included in that is 0. So instead of doing at least 1 and finding all of those possibilities, I do the opposite of that. So I'm doing the complement. I do 1 minus the probability of none. And then for conditional probability, that's what this is. I do that a lot with probability. I make a P there. So for conditional probability, you do the and over the given. So A and B over the given, which written this way, the probability of B given that A has already happened, A is the given. It might say given, it might say if in the question. That's all you got to do. Oh. Can't erase that. No. All right, there we go. Okay, here are some example problems. Of voters in a recent election, 57% were male, 64% were Democrat, and 35% were both male and Democrat. So notice these events are not disjoint because you can be both male and Democrat. What is the probability of voter chosen at random is female? So assuming two genders, we're doing 1 minus the probability of the males. What is the probability that a voter chosen at random is either male or Democrat? So to do this, we'll add our males plus our Democrats, but notice these 35% of people are being counted as part of the males and as part of the Democrats. So when we add these, we get a number above 100, but once we subtract 35, it's fine. So 86% are male or Democrat. Is being male or Democrat independent of each other? So if it is independent, then the probability of A and B equals the probability of A times the probability of B. So to check for independence, I just check to see if this is true. So I find A and B I already know is 0.35. A times B is 0.3648. Those numbers are not equal, meaning being male and Democrat are dependent. You can also check that the probability of B equals the probability of B given that A has already happened. I wouldn't do that in this case, but you could do that. You can also do it with the opposite. The probability of A equals the probability of A given that B has already happened. But in this case, this is the best method. Here's another example. The probability of rain on Monday is 0.3. Thursday is 0.4. These are independent. That means whatever happens on Monday doesn't affect what happens on Thursday. That might or might not be true scientifically speaking, but mathematically, that's what we're assuming here. What's the probability it rains on both days? So since they're independent, I just do Monday times Thursday. It does not rain on Monday. It's going to be 1 minus 0.3. It rains on Monday, but not Thursday. So I need yes Monday. So Monday is 0.3. And no Thursday. So it's going to be times 0.6 for the no Thursday. It rains at least one of these days. So that could mean it rains both of the days. So it rains on Monday and Thursday. Or it could not rain on Monday, but yes, rain on Thursday. Or it could rain on Thursday, but not rain on Monday. The only thing it doesn't include is not raining either day. So instead of finding all three of these possibilities, I'm going to do 1 minus this probability, because that'll be the same thing. So I do 1 minus the probability of it raining on no days. So 1 minus 0.7 times 0.6, which is 0.58. It rains on exactly one of these days. So that means it rains on Monday, but not Thursday. Or it rains on Thursday, but not on Monday, which gives you 0.46 when you calculate that out. Next is tree diagram. Tree diagrams are one of my favorites. They're really, really helpful in calculating big probabilities like this, especially when you get a lot of different numbers. The other kind we did was two-way tables. That's not in these set of notes, but if you struggled with two-way tables, make sure you go back and review that. But I'm going to focus here on trees. Only 5% of male high school basketball, baseball, and football players go on to play at the college level. Of these, so this is a conditional probability they're about to give us, only 1.7% enter major league. Of the athletes who do not play college sports, so this is another condition, only 0.1% enter major leagues. What is the probability a high school athlete will play professional sports? So you want to start with what you know for the whole population and then break it down into the two conditional probabilities. So the thing I know for the whole population is that 5% play college and the rest do not get to play college. And then after that, I know if they go to college, there's a 1.7% chance they go pro, so it's 0.017. Versus if they don't go to college, there's only a 0.1% or 0.001 chance that they go pro. The next step is to multiply your branches. Remember, we only use the numbers at the ends of the branches when we calculate the questions for a tree diagram. What is the probability a high school athlete goes pro? So we use the numbers at the end. These high school athletes went pro. So I just add those together. What is the probability a high school athlete played pro if he played in college? So that's a conditional probability. So I'm going to do the and over the given. So the and is that he played pro and he played college. So played college and played pro, that's my and. That goes on top. My given is that he played college. These two got to play in college. So I'm going to add those two together for my denominator. Once I type, so I'm doing 0.00085 over 0.00085 plus 0.04915. And yes, it is that number. It actually does work. They're asking you what was given in the question. And that's fine if you can see that, but I think you're less likely to make a mistake working it out like this. For the next one, what is the probability a high school athlete played in college if he went pro? So now the given is that he went pro. So he played in college and he went pro, so it's still 0.00085 on top. But on bottom it says if he went pro. So the given is that he went pro, which are these two numbers, which we already calculated up here. And when you type that in, you get 0.4722. Okay, I'm going to pause the video and just do two separate videos so it uploads faster, and so that you can review the one that you are struggling with the most if you want to watch them again later.